Okay, let's continue our discussion of isomorphisms by listing some properties. And some of these we've proven already, and some we'll show in this section. Remember that an isomorphism is a bijection, and it preserves the group operation. So that means phi of G1 dot G2. This dot denotes the group operation in G, is equal to phi of G1. I'll make a hollow dot here, phi of G2. And this group operation is the group operation in H. Now, first of all, we know it's a bijection, so it's not surprising that the orders of the two groups involved must be the same. If one is infinite, then the other is infinite. If one is finite of order n, then the other has order n as well. It shouldn't also be surprising that phi inverse is a isomorphism, because certainly phi inverse is also a bijection. And using this relation, we can show, or we did show, that the inverse function also satisfies a similar relationship. Two isomorphic groups, they both must be abelian, or neither one is abelian. That makes sense. We showed that in the last section. They both must be cyclic, or neither one is cyclic. So cyclic groups are only isomorphic to cyclic groups. Here's something new, which is quite important. If I take any element, any individual element of G, and it has order n could be infinite as well. Now recall what order is. It means that I can form the set G squared, G cubed, all the way up to G to the n, and there is some n where it reverts back to the identity. Of course, if it's infinite order, it never does, but if it's finite order, it always reverts back to the identity. And there are n elements in this set means that the order of G is n. Now it turns out that if you take the isomorphism and apply the isomorphism to any group element of G, you get another group element in H that has the same order. Okay, so you could say that isomorphism preserves order. Okay. The last one actually is a generalization of this and is even more important. It says that isomorphism preserves subgroups. If I have a subgroup in G, subgroup G prime in G, then phi of G prime, which is a set because you're taking phi of every element of G prime, this set is a subgroup of the image group H. And in fact, these two subgroups are isomorphic. Okay? And you have a bijection which preserves the operation. Okay? And in the spirit of self-discovery, these parts are proven by you. And here we outline a proof of the subgroup one. So I'll let you do that. And here's some exercises to illustrate these concepts. All right, now, what are isomorphisms good for? Isomorphisms are good for classifying groups. So what we're actually going to do is we're going to seek us standard groups that classify all groups up to isomorphism. Okay. For instance, if there's a group that I know very well, and I can show another group is isomorphic to that group, I can say, well, now I understand that other group because it's exactly the same as this group that I know. Let's see how this process works. First, we'll classify cyclic groups. Okay, this is a particular simple type of group generated by a single element. And it turns out that if G is a cyclic group of infinite order, then G is isomorphic to the integers. So there's basically, in some sense, only one cyclic group of infinite order, and that's the integers. There's any cyclic group of infinite order is essentially has the same behavior as the integers. And this proof is done by finding an explicit isomorphism from the integers to an arbitrary group. And the proof consists of showing that, in fact, this mapping is an isomorphism. You can see that it preserves the operation. Here we have addition in the integers, and here we have the group operation in group G. So we make this relationship. We show that this mapping is in fact an isomorphism. Okay. Here's an interesting consequence is that NZ, which is a subgroup of Z, is in fact isomorphic to Z. Kind of paradoxical, but those kinds of things do happen with infinite sets. If we go down to finite order, we'll find out that if G is a cyclic group of order n, a finite group, then G is isomorphic to Zn. Similar proof. Okay, so we've characterized cyclic groups both of infinite order and of finite order. Okay, so that takes care of cyclic groups. Now we'll be a little bit more ambitious and classify all finite groups, any group that's finite. And this is called Kelley's theorem. Kelley, very famous mathematician, one of the pioneers of group theory and abstract algebra in particular. And let's see. So what we're actually going to show is that, now I'll give you the punchline. It says all finite groups are, and this R means up to isomorphism, permutation groups. And this is one reason why we spent so much time with permutation groups, because if you understand permutation groups thoroughly, then in some sense you understand the structure of any finite group. Okay, so let's see. Let's go down and see how this construction works. Consider this particular group Z3. It has 3 elements. Here's the Kelley table. All right. Now, notice that this is kind of set up to give us permutations. Look at this first row, for instance. What does this mean? This means that if I add 0 to 0, 1, 2, I get 0, 1, 2. In essence, I'm defining a function from these column labels to the group itself. With the second row, it's the same thing. If I add 1 to each one of these group elements, if I add 1 to 0, I get 1. If I add 1 to 1, I get 2. If I add 1 to 2, I get 0. That defines a function from the group elements to themselves. It's a one-to-one onto function. In fact, it's a permutation. Same thing with this group element 2. If I add 2 to any one of my existing group elements, it defines a new group element that's mapped from the original group element. And you can see that the way this is set up, it's very well set up for tableau form. I can form a tableau for this permutation by taking the original column labels and taking the results what I get from adding 0 to each one of these original column labels. So I get 0, 1, 2, 0, 1, 2. For 1, I take 0, 1, 2. It's the same first row. The second row is simply the result when I add 1. Okay, so I have this representation of the permutation that occurs when I add 1 to every group element. And of course I can write this in cycle structure. It gives me this cycle structure. Same thing for 2, same process. Notice here we have 3 permutations. These 3 permutations in fact form a subgroup of S3. Okay. And this is actually how you do it in general. In general, you can associate each group element with a permutation. And here it is explicitly. If I take any group element G, then I can define a permutation on the elements of big group G. So A is an arbitrary element of big group G. The permutation applied to this element is simply given by the group element times the arbitrary group element. Okay, this generalizes what we showed with the group table Z3 above. This gives me a mapping from group elements to permutations, and that's specified by this. Phi of G, this is a big phi, but this serves as isomorphism. Phi of G is defined to be the permutation caused by multiplication by G. And then the rest of the proof goes into showing that in fact this function phi is an isomorphism. Now, we've seen before that 2 groups can be isomorphic in more than one way. This isomorphism takes G to a subgroup of S of order G. Now there's another possible isomorphism. I can associate each group element G with the following operation: multiply arbitrary group element by G inverse on the right. Okay. This will also give me a permutation of the group elements. So I can define this mapping from group elements to permutations by saying phi tilde of G is equal to the permutation caused by multiplying every group element on the right by G inverse. And we can similarly show that this mapping phi from group elements to permutations is one-to-one onto and preserves the operation. Okay, we'll stop here and go on with the next video.